Hello and welcome. In this video, we are going to look at the quality factor, bandwidth, and upper and lower frequencies of a series RLC circuit at resonance. So, the first thing they have us look at is our resonance frequency, and that requires our time constant for our circuit, and that time constant varies depending on the circuit you're working with. So in this case, our resonant frequency, FR, is equal to 1 over 2 pi, and then whatever time constant we have for our circuit. In this case, we have an R and a C in our circuit in series, and so we'll say that that's our time constant is our square root of L times C. We can calculate that out right now and say that we have 1 over 2 pi square root of our inductor, 2.2 millihenries, so 0.0022, multiplied by our really small capacitors, so 68 times 10. Times 10 to the, it's pico, so negative 12. That gives us a large frequency here. Let's write that out. Our resonance frequency is equal to 411,485. They want it in kilo ohms, so we'll round a lot of this off here, and we'll just say it's 411 kilohertz, not ohms. That is what we'll use here, so 411. Our quality factor depends on our XL value, and now that we found out our frequency, we can calculate out our XL. I'm going to keep accuracy if we can here. So our XL is what we want because our Q factor is equal to XL divided by our resistor value. Right, so we need to figure out what our XL is. We already have our resistor value. It's 13 ohms down there, so we'll figure out our XL here. And that is our 2 pi FL equation. We can plug that in. We now found our F, and it's going to be our resonance frequency for our F, so FR. So we'll just plug that in here. Say 2 pi times our frequency of our answer. So we'll just pull in that answer that we just got. And then we will also multiply by our inductor of 0.0022. That gives us this number here. Plug that in, it's 5,688. And so that is our XL, that's an ohmic value for our XL. So we'll use that in here. So 5,688 ohms divided by our resistor value of 13 ohms. And that should be our quality factor. So 5,688 divided by 13 gives us 437. And there's no units for the quality factor because it's a factor of two numbers. 437 is our answer for that one. Our bandwidth in kilohertz is going to directly depend on our Q factor and our resonance frequency. And so we'll write that in. So our bandwidth, BW, equal to our resonance frequency, FR, divided by our Q factor, which we just got. So now we can plug both of those numbers in. We can say that we have 411,485, that's our frequency, divided by our Q factor of 437, and that gives us 942. And in this case, they want it in kilo ohms, so we'll put a 0 point in front, 0.942, and that gives it our kilohertz. Hertz. We'll plug that number in, so 0.942 kilohertz. After that, we'll find our upper and lower critical frequencies. We'll send this out. Our lower critical frequency takes our resonance frequency of 411,485 and subtracts our bandwidth divided by 2. So our bandwidth is 942 divided by 2. So this is our lower critical frequency. We want to put in kilo ohms, so we'll say 411. And then our upper critical frequency is just this added to it. So instead of minus, we'll add it, and we also get 411. We'll see if that's accurate. And there we go. All right, let us know if you guys have any questions.